Hello and welcome back to our class on computational finance. We are now at chapter 4, asset models, in which I will try to give you an overview of the most important asset models, stochastic processes used to model asset prices. And we'll start with a very basic wiener process and then move on to the geometric Brownian motion. I will show you how these models are used in the Black-scholes model, and then in the end, in chapter 4.3, I want to show you Poisson jump processes, which are a little bit more realistic than wiener processes or geometric Brownian motion. And these processes need to be simulated, and this needs to be done with a computer in order for those simulated asset prices to be used in, for example, the Black-scholes model. So this is what we are trying to do here, and we need efficient algorithms to simulate from these processes. So let's start. You can read about this in the Albrecht Maurer textbook, or you can have a look at chapter 5 in the Vollmer. This is a typo. Vollmer sheet. The colleague's name is Alexander Sheet. Vollmer sheet, Stochastic Finance. This is a book written by two mathematicians for math students. So it should be too technical for business students. But if you're more interested in the subject, you can have a look at the Vollmer sheet book, which is actually the standard textbook for stochastic finance in discrete time. Okay. Now, we've talked about portfolio theory, we've talked about optimization, and we've seen different models for the optimization of a function. What we are now trying to do is we are trying to come up with models for the time evolution of stock prices, for example. And for this, we need to have a closer look at so-called time continuous processes, zeitstetige Prozesse, stochastische Prozesse. Could also be time discrete, but we are trying to model prices in continuous time. So we are at least theoretically able to observe a change in the price at an infinitesimally small change of time. First of all, we now need to be clear about what is a stochastic process. And some of you might know this, but I'll give you a short reminder and a definition. Now, a stochastic process is simply a set of random variables, and each random variable is indexed with a running index t. T stands for time. So for every point in time in a set of time indexes, we have one random variable. Meaning what? We could start, if we were to do this in discrete time, we could say, okay, we have a set 0, 1, 2, 3, 4. So we have 5 points in time, and then the set x0, x1, x1, x2, x3, and x4. This is a stochastic process. For every point in time, 0, 1, 2, 3, 4, for every point in time, we have one distinct, unique random variable, x0, x1, x2, x3, x4. So this would be a very simple example for a discrete stochastic process. If we now have, for example, not 0, 1, 2, 3, but if we now have all numbers, t, let's say larger or equal to 0, then of course we have x0 and so on and so on, and this is an infinite set. Then this would be a time continuous process. Say this in German again. Ein stochastischer Prozess ist erstmal definiert als eine Menge von Zufallsvariablen. Und üblicherweise macht man das natürlich so, dass man sagt, man hat Zeitpunkte, und für jeden Zeitpunkt gibt es eine Zufallsvariable, x0, x1, x2, x3. Wenn die Menge diskret ist, ist ein diskreter, zeitdiskreter stochastischer Prozess. Wenn die Menge unendlich, überabzählbar, also überabzählbar unendlich groß ist, dann ist es ein zeitstetiger Prozess, weil ich für jede kleinste Änderung in der Zeit sofort wieder eine neue Zufallsvariable habe. Okay, so this is a stochastic process, xt. And we'll have a look at the most important model for the time evolution of stock returns, and also in mathematical physics, which is the so-called Wiener process. And then we can derive from the Wiener process the so-called geometric Brownian motion, and this is the model used in the Black-scholes model for option pricing. And then we'll later on derive models, especially the Black-scholes model, which we can use to price options. But in this chapter, we already learned the basic ingredient and the most important ingredient, which is the Wiener process and the geometric Brownian motion, which is the assumption made in the Black-scholes model for the stock price evolution, for the time evolution of the underlying price. And then, last but not least, in the end, we'll also have a look at jump processes, which are an extension of the stochastic processes we've seen before. So we'll start with the geometric Brownian motion and the Wiener process. Why do we need this? We need a sophisticated model for the time evolution of stock prices. Again, a small typo. Let me just correct this. Of stock prices. Why? For example, in the Black-scholes model, we need a model, a stochastic model for the time evolution of the stock price in the future. Now, since numerous models, including the Black-scholes model, present future price evolutions as random walks, we'll first discuss this tool in detail. So what is a random walk? A random walk can be described as follows. Can be clearly described. Another error. You start at one point and you walk a random distance in a randomly selected direction. And then the random walk corresponds to the sequence of these steps. So for example, you start here. This is a random walk in 2 dimensions. Clear, x, y. So we start here and we take a step to this point. Then here, 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 so on and so on and so on. And as you can see, this is a random walk in the sense that you take a random step length into a random direction, and I could continue doing this and so on, and we get a random walk. Now, one important question is, how far does such a random walk get you after n steps? So how long is the so-called end-to-end vector r? And the end-to-end vector r, let me see this is the end-to-end vector. I started here, and this is where I ended up. So the question is, how long is this end-to-end vector? Let's call this r. And not surprisingly, in expectation, the length is 0. So if you start, for example, here, and you walk into a random direction with a random step length, well, it might get you here, but this is one example. The second example could be like this. So we have 1 point here, 1 point here, and the random, the end-to-end vector, sorry, I took the wrong line here. So this is one end-to-end vector, this is another end-to-end vector, this could be another one, this could be another one. And as you can see, if you only have more and more random walks, the expectation is 0. A random walk will not get you anywhere because it's completely random. Furthermore, if we square the length of the end-to-end vector, we actually get in expectation this value, which is proportional to n. So the expected value of the square of the end-to-end vector is on average proportional to the number of steps of the random walk. So for example, this would be 1, 2, 3, 4, 5, 6, 7 steps. Okay. So what is the variance of the end-to-end vector? Well, if we know that the expectation of r is 0, if we square this, this still gives us 0. And if we take the expectation of r squared, then it is proportional to n. So we know that the variance of the end-to-end vector is proportional to n. And this is interesting for one simple reason. This is actually the explanation why in many risk models that you might have seen already, you have a very simple conversion formula, for example, from the 1-day to the 10-day valued risk. And what happens is that you use a factor, the square root of the number of days, to transform the 1-day to the 10-day var. And the reason is, well, actually the variance is, if you assume a random walk, the variance is proportional to the number of steps. In this case, this would be 10 days, so 10 steps. So you take the square root of that. Okay. Now, this above-mentioned proportionality of the variance or the standard deviation of r squared is also can be explained by the so-called self-similarity of a random walk. What does this mean? It means that if you take a random walk that looks like this, then actually, let me use another step, then this, this here, this vector is again, can be seen as the end-to-end vector of a different random walk. So it could look like this. So this is again a different random walk. Then every step of one random walk is again the end-to-end vector of a smaller random walk. And what else do we have as properties of a random walk? Well, the end-to-end vector is normally distributed with expected value 0 and a variance b squared times n, where b squared is calculated from the sum of the expected length of all those individual step lengths of the random walk. So what does this mean? First of all, the end-to-end vector of such a random walk is, at least the length, is normally distributed. The expectation is 0 and the variance is proportional to the number of steps. And this is very important because it means if you assume for such a process that it is a random walk, which can be many processes, you suddenly get the normal distribution for the length of the end-to-end vector. And if you now think about a random walk in one dimension, you see that, for example, if it is in one dimension, for example at the x-axis, you can see that it goes up, goes down, goes up, goes down, goes up, up, down, down, up, down, up, down, up, up, down, up, down, up, down, for example. And suddenly you see that if you have on the x-axis the number of steps n, and on the y-axis the change in the process, you suddenly see why a random walk can be used to model the time evolution of changes in a stock price. And for this, it is quite interesting now to see that if you assume a random walk or a stochastic process that is a random walk, suddenly you get the normal distribution for the evolution of your stock prices. And this is what the Wiener process and the geometric Brownian motion will later on do. They will assume a certain type of stochastic process, which will be random walks, and suddenly you get a normal distribution for, we'll later on see, for the log returns. Okay, so the use of a random walk implies the assumption of a normal distribution for the associated end-to-end vector of that random walk. Okay, now we want to model the changes of a stock price via a random walk and derive the properties of this model. And first of all, we need to find a price for a stock. The price can only increase or decrease. Thus, as I've shown you here, we are looking not at a random walk in 2 dimensions where the process can change in 2 dimensions, but we are looking at a random walk in 1 dimension. It can only go up and down. Now, the time dt elapses per step of the random walk, and during the whole random walk from small t to capital T, the time that elapses is capital T minus small t, so n times the step length in time dt. The random walk models the changes in the stock price, that is the change dSi in the ith step, and this is defined as the difference between Si, the stock price right now, minus the stock price one period before that. Okay. Now, if the price itself were a random walk, the individual steps dSi would also be random walks because of the self-similarity. However, a security with a price of 1,000 euro would then have the same price fluctuations as a security with a price of 10 euros. Thus, the absolute changes should not be considered, but we should focus our attention when using such a model on relative price fluctuations. Now, one could think of discrete returns being the relative price fluctuations. So we could think about using Si divided by Si minus 1. So these could be the steps of random walk. However, it then turns out that the end-to-end vector, if you want to call it this way, S capital T divided by S0, it cannot be represented as a sum, but only as a product of the individual steps. However, we've seen that for the end-to-end vector, it must be that actually the end-to-end vector is the same as the sum of I plus 1 plus and so on. So if you add up all these vectors, you should get the end-to-end vector. This cannot be done if you're using discrete returns. Thus, these ratios Si divided by Si minus 1 are completely unsuitable as a model for a random walk. Okay, so the solution is quite simple. Instead of using discrete returns, we simply use log returns, returns in continuous time. So we not only take the difference between the prices, we take the difference between the log prices. So this gives us the log of price Si minus the log of the previous price Si minus 1. And then you can see if you take the difference of these log prices, you get the log return, dln/Si. So this is used and modeled as a random walk. And this is also why in these models, in continuous time, obviously we are led to models that rely on log returns rather than discrete returns. Now we have the following. If you take the logarithm of the last stock price divided by the first stock price, you have the difference between S capital T and the log of S0. And this is also the same and equal to the sum of the log returns. Thus, the sum of individual steps, they add up to the required end-to-end vector. So the requirement for using a random walk is given and is fulfilled. Now, next, we'll define a wiener process. So far, we've only said, okay, we want to model this as a random walk. So we need a more concrete example of a stochastic process, and this is the wiener process. So wiener process is a continuous stochastic process that has normally distributed independent increments. Increments are the changes from, let's say, I to I plus 1. So the difference, like this, or actually like this, in the process, the difference is called an increment, also changes or growths. So the increments are normally distributed and independent over time. So if a wiener process changes dt by an amount dw over time, these changes are normally distributed with expected value 0, variance dt, and you can describe this. You have a wiener process, and the change in the wiener process is normally, the changes are normally distributed according to x, square root of dt, and x is a standard normal distribution. So that's the definition. That's the definition of a wiener process. So a very simple stochastic process in which the changes in every step of time the changes are normally and independently distributed. So that's a Wiener process. So a stochastic process is called a Wiener process, sometimes also called Brownian motion. This is not quite correct. The Brownian motion is actually the phenomenon in physics that can be modeled using a Wiener process, but people usually just call it Brownian motion. So xt is called a Wiener process if the changes, the increments xt1 minus xt0, xt2 minus xt1, and so on, if they are stochastically independent, if those increments, those changes for any leg, if they are normally distributed according to this, so this is the expectation, and this is the variance, and if those increments, if the distribution of those increments only depends on the leg h, so the time difference from t to t plus h, if this only depends on h and not on the position of xt, then we have stationary increments, and then this is Wiener process. So increments are stochastically independent. The increments, the changes are stationary, and they are normally distributed with the expectation and the standard deviation or variance depending only on this leg t minus s. See that actually this is the expectation, and this is obviously the variance of the normal distribution, but this here, this parameter, and this here, they are called drift and diffusion of the process, because these are not, you don't have just one expectation, you don't have one variance. Variance and expected values can change over time, so you don't have one, but the parameters mu of t minus s and sigma squared of t minus s, they stay the same for different, they only depend on the lag. So we don't call them expectation or variance, but we call them drift and diffusion. Obviously, these two parameters govern the expected values and variance, but in the context of a stochastic process, we call them drift and diffusion. Okay. So let's continue. The Wiener process can also be written in the following way. xt is w0, a starting point, plus mu t, the drift times time, plus the diffusion times the square root of t times zt, which is a standard normal distribution. We then have that the covariance between 2 points in time, st, is the minimum of s and t times the diffusion, and then we can see that the expected value of 1xt is w0 plus mu, the drift, times t, and the standard deviation is the diffusion times the square root of time. And the standard Wiener process is then given by, if we start at 0, if we have no drift and uniform diffusion, that is, in other words, xt is simply a standard normal distribution times the square root of the point in time we are looking at. So if we start at 0 and we have our timeline, you can see that actually we have a standard normal distribution times the square root of time. Yeah? So this is t, and this is not just z. This is not an unconditional distribution xt, but you have to multiply the standard normal distribution with the square root of time. Okay, so next we want to make this a little bit more practical. We want to simulate a path of a Wiener process. We want to simulate one example for a Wiener process. We start out with rand n, state and 100. We need to reset the random number generator for a normal distribution. And if you were to repeat this using this this MATLAB code on your computer, you would get always the same results. I don't think I've mentioned this before, but for a computer there is no such thing as a random number. A computer cannot do random. Let's be quite clear. No computer can do anything that is random. The computer can only do something that is pre-written and programmed. So what these computers do is they use pseudo-random number generators. these numbers that appear to be random, they are random, but only at first sight. They always have the same starting point. So you can use this starting point here, let's say here, and then you get random numbers. So if you only look at these numbers, they will appear to be random. However, you can repeat this and you will get the same random numbers. So they are only pseudo-random. So we have to reset our pseudo-number generator in order to replicate our results. And this is what we do in the first line. Then we say, okay, we have capital T equal to 1. We have 500 steps. So every step has a length of 1 over 500. dw is a vector of zeros. W is a vector of zeros. And we start out with a square root of dt times a rand n, the random number generator. And then W1 is initialized with dw1. And then we have a for loop and say the change in the process is square root of dt times a random number from zt, the standard normal distribution. And then the next process and the next state of the process is just previous state plus the change, and then we plot it, and what you see is we start out 0, and this is one simulated path of a Wiener process. Pretty much looks like a stock price, so this is nice. We can repeat this 5 times, 10 times, 1,000 times, and then we would get maybe something that starts again out in 1, but something that looks like this. And another one, and another one, and so on. So this is a path, a simulated path of a Wiener process. Now next, we consider an infinitesimally small time change, dt. So again, we are in continuous time. And we have the log prices, d, ln, st. And we assume under a random walk that we get the following. Under random walk, we get that the log changes in the stock price, the log returns, they will follow a Wiener process, a standard Wiener process, times a parameter sigma. And the variance of the process here is then given by the squared value of the diffusion times the change in time. So this is one result. If we assume a random walk, we get a standard Wiener process times the diffusion. Now this model for the time evolution of log returns so far only has one parameter, that is volatility or diffusion. So hence it is not yet flexible enough to represent the actual changes, because you can see here they will all evolve around 1. But what we might want, that we not only have diffusion, but we have a positive or maybe a slightly negative trend, so that the time evolution will look something like this. Or something like this. So that we have a positive or negative drift. So we add an independent drift into the mixture, and we get our model with the Wiener process that we say we have the log returns, and the log returns are modeled as expected value drift mu times the change in time plus volatility times the Wiener process. And adding such a deterministic term only changes the distribution of the log returns or the individual steps in the expected value. However, the distribution is still a normal distribution. So assuming even a Wiener process to which we've added a drift, this doesn't change the distribution, it changes only the expected value. So we still have normally distributed log returns. Then you can also add non-constant drifts and volatilities as an extension of the model, and the drift could be a function of time and stock prices. Then, for example, we have not only mu as a constant, but mu of, let's say, st and t. This would be a non-constant drift, same with volatility. We could also say volatility. and this wouldn't change the distribution. And on a side note, you can see that the log prices are normally distributed. The price itself is log normally distributed under the assumption of a random walk or a wiener process. Okay. Again, a reminder, what is the difference between a random walk, a wiener process, and a Brownian motion? Now, the wiener process is a stochastic process, which has a similar behavior to Brownian motion, which can be used to model Brownian motion, which is the physical phenomenon of a minute particle diffusing in a fluid. For example, if you were to throw a can of oil into a box of water, then you would see how maybe, or if you probably, this is something different, maybe not oil, but if you were to take red water and put it into blue water, you would see that they would mix, and the phenomenon, how these particles diffuse in a fluid, this is Brownian motion, and this can be modeled by a Wiener process. So sometimes it's called synonymously, it's used synonymously. However, strictly speaking, the first one is a model, the second one is a phenomenon. And the Wiener process is the scaling limit of a random walk in dimension 1. This means that if you take a random walk with very, very small steps, you get an approximation to a Wiener process, and less accurately to Brownian motion. So every time you hear in finance we're using a random walk assumption, we're using a Wiener process, we're using Brownian motion for the stock prices, you now know it's all the same. It's basically a Wiener process. Okay. So we've now assumed a stochastic process in the form that the changes in the stock price or in the log stock price are given by a function A. This is the drift. We don't know how A looks like, but this is a function given A, and a function B. A times the change in time, and B times standard Wiener process, and X is normally distributed. Okay, right this way. So this is the model we are using for the changes in the stock prices. This is a geometric Brownian motion. So a stochastic process follows a geometric Brownian motion if we take this model, which is a very general definition of a diffusion process, a process that has a diffusion process and a diffusion component and a drift. And if we now add the stock price itself, or the process itself, at this point here and here, we get a geometric Brownian motion in differential notation. So this is the same as before. We have a constant mu and constant s, sigma. And if we now multiply this with the process itself, we get a geometric Brownian motion. Now, if we were to use m equal to the drift minus the diffusion divided by 2, this would imply that, again, if we now take the difference in the log prices, we get m dt plus sigma dw. So m, in this case, describes the current continuous time mean return, and mu the current mean discrete return. So what we see is we assume a diffusion process for the change in the stock price, and thus a geometric Brownian motion for the stock price here gives us a Wiener process for the log prices. So it's all related, really. So a quick summary. We assume that the stock price follows a geometric Brownian motion. Thus, the changes in the stock prices satisfy dst equal mu st dt plus diffusion or volatility st dwt, which means that the log returns follow a Brownian motion. We now know this is a Wiener process, and as a result we have the assumption of the geometric Brownian motion for the stock prices gives us log normally distributed prices and log returns which are normally distributed. And in many textbooks you will see that people say, okay, we assume a normal distribution for the log returns. which isn't really correct because the assumption isn't the normal distribution for the log returns, but it's the assumption of a geometric Brownian motion for the stock prices, which then gives you Brownian motion for the log returns and a normal distribution for the log returns. Okay. So the important question is now which stochastic process a function f in the stock price s and in time t follows. In particular, what change df is induced by the change ds. So we have the stock price st and we have time, obviously. And the question is, we have a given function f in st and t, and how is it distributed? What kind of process do we get? Well, you can see that we are moving now to the Black-scholes model, and the answer is actually given in the Black-scholes model and in the required math before. It's Ito's lemma. That gives an answer to this question. So we get Ito's lemma, and we are looking at the change df of a function in s, which is a stochastic process, and in time t. We are performing a Taylor expansion. That is, we represent the function using its Taylor series. For df, we get the change in the function in the stochastic process is given by. You can do this at home. This is the Taylor expansion. You get the partial derivative. Actually, this is the total differential. And you can see that it goes on and on and on. You have the first partial derivative, the second order partial derivative, and so on and so on. And you can see that you have now the squared value of the change in the process and the squared change in time, and so on. And you can summarize this as follows. This is given here. And the important thing now to see is that actually everything that comes later on has the change in time. For example, to the power of 3, to the power of 4, and so on and so on. And the change in time dt is infinitesimally small. So if you square it, if you take the third power and so on, this is close to 0. So everything that comes here is summarized in this. And in essence, you can say that this becomes 0 because simply everything is multiplied with dt taken to the second, third, fourth power and so on. So it will vanish. So what you get is this here. This is Ito's lemma. It says that you can approximate the change in a function in a stochastic process by these two factors. And they obviously depend on the partial derivatives of s. And we can see something else. If we now expand this, first of all, we need to see, well, we have the expectation of dw and dt. So at some point we have the Wiener process squared. So the expectation of the squared change in the Wiener process is dt, and the variance is proportional to dt squared. So in linear approximation, in the change of time, the variance of the squared Wiener process disappears. So in essence, this becomes deterministic. But if the variance is 0, then the term dw squared can be assumed to be deterministic, and it can be set equal to the expected value, which in this case is dt. And if we now say that the change in time is proportional and distributed according to the square root of dt, and if we ignore all values that are smaller than dt, especially squared, taken to the third power, and so on. So what we get is we can substitute this, we can leave out this, and so on. And what we finally get is Ito's lemma, which states, mathematically imprecise, but it suffices for our purposes, that the infinitesimally small change of a function in a stochastic process s and t with the in continuous time with the change dt going to 0 we get that this change in the function is approximated by the partial derivative of f with respect to the process times a function a plus the partial derivative of f with respect to t plus and so on the second partial derivative times function b squared dt plus la 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 dw. And what is so striking is that now this tells us that the change in the function f is again a diffusion process. You have something la 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 dt plus la 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 dw. So you have one very complicated drift function times the change in time plus a less complicated diffusion function times dw. So a, delete this, a is mu, b is set to sigma, and we see that now this is actually again a diffusion process. This is why it's also called an Ito process. Striking result, if you assume a diffusion process for S, any function in S, the change in this function in any function is again a diffusion process. Okay. So Ito's lemma can further be reduced to this. And you can see we have the partial derivatives with respect to t, s squared and s in here. The difference is here that this is now not the Wiener process, but the process st itself. And using this, we can now derive the Black-scholes pricing formula. Okay. Yes. So next, let's have a look at the Black-scholes-Merton model and how these models for the asset prices are used in the Black-scholes-Merton model to derive a price for a derivative. So we want to specify the value of a derivative on an underlying stock S at a time t by, let's say this is a function v of S and t. The underlying stock follows a stochastic process dst. Actually, we can leave this out. We can simply assume that we have a stochastic process dst, which is a diffusion process. Then we now know that if S is a diffusion process, then dV is also a diffusion process with slightly different drift and diffusion. And this is given via Ito's lemma on this slide. The change in the option price is given by the partial derivatives here, which form the drift, and the diffusion dt and ds. Now, you might ask yourself, what is this partial derivative? Well, remember the start of our lecture. Actually, these are, not surprisingly, the so-called, these are the so-called Greeks. Okay. Now, small side notes. The representation of Ito's lemma. It may sound somewhat artificial at first glance. So why should one want to consider a general function? But actually, this is the beauty of it, because if you think about this, we haven't said anything about what kind of function f is, or v. We only said that this is a function in the underlying price. And the nice thing now is that actually we can use this model to price any derivative, any function in S in the underlying price. And this is also one reason why the Black-scholes model can actually be applied to any, in theory, to any type of derivative, not only stock options, but any derivatives. Okay. So next, we have made our assumption of a diffusion process for the stock price. We've used Ito's lemma to see that the derivative price is again a diffusion process, but with a slightly different diffusion and a slightly different drift. And we now construct the following portfolio. The portfolio is called pi. It's one derivative long. We buy the derivative and we short sell delta number of the underlyings. So the portfolio value and the change in the portfolio value is given by the change in the option price minus delta, the change in the underlying. And we now know, well, this is actually given. The S stays the same. And we now know from Ito's lemma that the change in the derivative price is given by this. So if we simplify this a little bit, we can see that this is a term that only depends on time, and this here, which depends on the change in the underlying price. Now this here, the first part, all this is deterministic. The second part is stochastic because the change in S is stochastic. The question now is, how can we make this portfolio risk-free? Well, it is risk-free if the change is deterministic, if it's zero, or if it's only, it doesn't need to be zero, but if it's deterministic, if it only depends on time. So what we need to do is we need to make this term here disappear. How do we make this disappear? Well, very simply, if the number of underlyings, delta, for the short sale is chosen according to the partial derivative of the option price with respect to S. And this is actually what we call a delta hedge. If we use the number of underlyings that we sail short, if it's chosen to be the option delta, the partial derivative of V with respect to S, then this is what we call a delta hedge. This is a perfect hedge. It reduces risk to zero because suddenly the change in the portfolio value becomes deterministic. Then, however, if with the delta hedge the portfolio price is completely risk-free, we should see that in an arbitrage-free market, this portfolio, which is deterministic, which is risk-free, should pay the risk-free rate. So if we use the risk-free rate R multiplied with the initial portfolio value and the change in time dt, then for arbitrage reasons, this needs to be equal to R pi dt. And this is the final step in the Black-scholes model. You take a portfolio that consists of one underlying long, delta number of underlying short. You make a perfect hedge, you make a delta hedge, and with a delta hedge the portfolio should pay the risk-free rate for arbitrage reasons. And then this is the Black-scholes stochastic partial differential equation, the SPDE. So if you put all this into this equation, if you solve for zero, this means that for arbitrage reasons, the return per time from a delta hedge portfolio consisting of one option, one derivative long, and delta underlying short, it must be equal to the return per time of a risk-free investment in the same amount of the portfolio value. This is not the this is the Black-scholes equation. And the question now is, how do we get the Black-scholes formula from this equation? For this to understand, you need to know what a differential equation is. And I would urge you to look this up if you don't understand this on Wikipedia. It's described everywhere in the internet. A differential equation in an ordinary differential equation could be something like f of x derivative equals f of x, or something, and if we write this with y derivative equals a function in x and y. And one example could be that the derivative, the first derivative, equals function itself. We are now looking for a function that solves this ordinary differential equation. One solution is obviously the exponential function. Another solution is f of x being 0 constant. So you can see that for this ordinary differential equation, you have more than one solution, sometimes infinite solutions. And what you see here is simply a stochastic version and a partial differential equation, which means that this is a function in more than one variable and you have partial derivatives in the equation. So we are now looking to solve this partial differential equation, and we need, as a solution, we are looking for a function. Now, how can you solve this, for example, here and decide whether it's the exponential function or 0? Well, you need a starting value. In German ein Randwert. Das ist ein Randwertproblem möglicherweise, dass Sie dann sagen, y of 0 equals 1. In this case, you can see that this has to be the exponential function and it cannot be the 0 function. So we need a starting value for to get the solution of such a partial differential equation. Before moving on, let's summarize the assumptions. In the Black-scholes model, we've assumed a log-normal random walk, a risk-free investment. The underlying does not pay dividends. We can do delta hedging in continuous time without arbitrage and without transaction costs. And then we get the Black-scholes stochastic partial differential equation. Now, the differential equations usually have an infinite number of solutions, and these solutions have functions as solutions. These differential equations have functions as solutions, not single numbers. So in order to derive a definite solution, we need to add additional boundary conditions, Randwertbedingungen. And for example, the initial value condition for an option is its payout profile P. For example, for the option value, you get the terminal maturity date here, you get what it pays out. So the payout function is the initial, or actually the initial terminal value condition for solving this partial differential equation. Yeah. And now we need tools from mathematical physics. We don't do this ourselves. Now, mathematicians tell us that the Black-scholes stochastic partial differential equation can be converted into something that is called the heat conduction equation or the diffusion equation, die Wärmeleitungsgleichung oder Diffusionsgleichung, and the solution is given by this. As you can see, the solution for any derivative still depends on the payout profile and it includes an integral. So this is the exact solution of the option value. So by inserting, we can now insert the payoff profile of the respective derivative and then solve for this integral, and we get the pricing formula for this derivative. And this is where it gets tricky. For some kind of derivatives, for example, a plain vanilla call where the payout profile is quite simple, yes, we can solve this integral. If you have a so-called exotic option, we cannot solve this analytically, and we need to use simulation methods, and we need to use a computer to approximate this integral. And then we get the solution. For example, here you can multiply this. Actually, you can do this on a sheet of paper and solve for this integral. What is interesting is, I think, the pricing formula, and you might know this from previous lectures on derivatives. For a plain vanilla European call option, the arbitrage-free price is given by this function. Stock price, current stock price times phi of D1 minus strike discounted times phi of D2, and D1 and D2 are given by this. So that's the Black-scholes pricing formula. The analytical solution can also be found for a put or for a digital call with slightly different payout profiles. The simpler, the easier the payoff profile is, the more likely it is that you will have an analytical solution for the Black-scholes partial differential equation. If it's more complicated, it's highly likely that you cannot solve this integral analytically. So finally, we want to analyze the Black-scholes price of a European call option in more detail. Of particular interest here are the dependencies of the price on the model parameters, and these are the Greeks. And in practice, these sensitivities are actually of greater importance than the price itself, because everyone is using these instruments for hedging purposes. And these partial derivatives, as I mentioned before, they are the so-called Greeks. So the first one is the option delta. It's the sensitivity to the share price, and we've seen that it's used in delta hedging for the perfect replication of the call option in the Black-scholes model. Then we have the option gamma. The option gamma is always positive, and these large values, it's the second partial derivative of the call price with respect to the stock underlying price. And large values of gamma rise in price ranges where the delta changes rapidly and where frequent changes to the delta hedging portfolio are required. And approximately the risk of a semi-static hedge can be further reduced over a short time window by constructing an overall portfolio that is gamma neutral. So it's relevant for the necessity to rehedge. Then we have theta. Theta as in t, as in time. It's the sensitivity of the option price on the maturity. And because of theta being larger than zero, the arbitrage-free price of the European call option is a growing function in terms of the maturity. And we have the option rho and the option vega. Now, the vega being not a Greek letter, but it's considered one to be here in the Greeks. And it's the sensitivity to the option, to the underlying volatility. Okay. So these are the Greeks. We also see the so-called leverage effect. For call options, the absolute change in value of the option price is always smaller than the corresponding change in the share price. That's the leverage effect. And at the same time, the relative change in value of the option price is greater in amount than the relative change in the share price. And this is what can be interpreted as a leverage effect for a call option. Then we distinguish the volatility skew and smile and historical and implied volatility. Now, European call and put options are traded liquidly for almost all blue chip stocks on major exchanges. And to model the same prices in the Black-scholes model, you need the current stock price, strike, maturity, interest rate, and stock volatility. Now, if you use all but volatility as fixed parameters in the Black-scholes model, you obtain a price formula for a European call option depending on the volatility. So it's a function of volatility. And then you can distinguish historical and implied volatility. Historical is simply the volatility you observe on the market. That's real, and basically real and reality volatility. Implied volatility is if you take the option price and reverse engineer the volatility implied by the Black-scholes model, then you get implied volatility. And for different strike prices and maturity, we can then determine the implied volatility and investigate the dependence of the implied volatility and on the strike and maturities. And a dependence on maturity, the term structure, and a dependence on strike, either a smile or a skew, a volatility smile, can be observed. And the dependence of implied volatility on strike and maturity is further evidence that the Black-scholes model does not correctly describe the reality in financial markets. And in a Black-scholes model with a given parameter vector, there is only one volatility, which then determines the prices of all call options. Consequently, implied volatility would be a constant. However, it is not in reality. So if the Black-scholes model was valid in reality, implied and historical volatility would correspond, but actually there are large and smaller differences from time to time. Okay. I think that's enough for today. That's a lot to digest. I will stop here before the jump processes and talk a little bit about the Black-scholes model in German after having stopped the recording. So if you're watching this, thank you very much for your attention, and see you in the next video.